In this presentation, we will introduce XIRVIO, critic-guided iterative refinement for visual-inertial odometry with explainable adaptive weighting. To begin, XIRVIO makes two notable contributions. First, XIRVIO's core innovation is the critic-guided iterative refinement. While the iterative refinement technique has been explored elsewhere, many of the times it's based on an assumption where the final iteration is the most optimized output. For XIRVIO, we bring this idea further by not only performing iterative refinement, but actually evaluating which output of these iterations is the most optimized one. As XIRVIO employs a GAN architecture, we can first use the generator to iteratively produce multiple incremental updates. Then, we feed this post estimate of each iteration into the critic to see how real each post estimate is. This approach allows XIRVIO to utilize critic's feedback during inference to determine which post is the most converged solution and will be selected as the final output. The second key aspect is the policy encoder, which handles what we call self-emergent adaptive weighting. The model autonomously learns to weight each sensor dynamically without any supervision, or in other words, any extra training objectives. For example, XIRVIO may learn to favor inertial inputs during rapid motion, or rely more on the camera when visual features are clear. This process is both automatic and explainable. By examining the weights, we can see exactly how and why the model behaves in a certain way under a given context. This explainability can be highly beneficial for safety-critical visual odometry applications, as you want to ensure the model is behaving as expected in your operating window. Now, let's take a look at how XIRVIO works. First, XIRVIO takes in the image inputs together with the IMU inputs. These sensory inputs will then be encoded by the feature encoder. Next, the encoder features will branch out and pass through the policy encoder, which calculates how much weight to assign to each sensor. This step is self-emergent, meaning that the system learns on its own when to trust the camera more, especially under clear, well-lit conditions, and when to rely heavily on IMU data, such as during rapid maneuvers or low visibility moments. The weights from the policy encoder will be multiplied onto the original encoder feature, forming our final latent features. After that, a generative iterative post transformer predicts a post estimate in multiple steps. Instead of generating a single guess, the model produces a sequence of incremental improvements, refining the post at each iteration. Once the model reaches the number of maximum iterations defined, the model will output post estimates from all iterations. We feed them into the GAN critic, together with the weighted encoded features. This critic acts much like a learned judge, scoring each iteration of the post for its realism. By relying on the critic's feedback during inference, the best scoring iteration is chosen as the final output. Now, let's visualize XIRVIO's model performance with the Kitty dataset. We can see that the model learns to favor the IMU rotation during low speeds and corners. We can also see that the optical flow is favored during low to medium speeds, especially in a steady straight line. As the speed becomes higher late in the sequence, the model learns to favor the IMU translation heavily. One interesting thing is that the optical flow weight fluctuates even when the vehicle is stationary. If you look carefully, you can see that the optical flow rises whenever there's a vehicle passing by. This is the end of our presentation. Thank you very much.